kPa, right? So that saturation pressure varies by a factor of 10, okay? So what that's saying, that saturation pressure, these numbers from 0.611 to, oops, not that high, to 5.6291, that is what's on the bottom of that equation. That's PG, okay? So the bottom of this number here varies greatly with temperature by a factor of 10, okay? So what that's saying is the reason why relative humidity is not a good measure of how much water is in the air is because if it's really cold outside, you can have a very high relative humidity, but you really don't have that much water in the air, okay? You really don't, okay? But if it's hot outside, you can have it be fairly muggy and fairly high amount of water. A lot of water can be in the air with, let's say, 50% humidity. If it's 50% humidity and 80 degrees Fahrenheit outside, there's a lot of water in the air. If it's 90% humidity and it's only 40 degrees Fahrenheit, there's not nearly as much water in the air. Okay? So just because you have a higher humidity doesn't mean there's more water. You can actually have higher humidity and less water because of the temperature. Okay? So relative humidity is not, it's not a great measure because it can lead to a lot of confusion amongst people. But it is something very common in terms of measurement of humidity. Okay? Now the one that's a better measurement of the actual amount of water that's in the air is dew point. Okay, and that's another one you may have heard of. The dew point, okay, the dew point temperature is the saturation pressure, okay, sorry, is the saturation temperature at that vapor pressure, okay? And so basically you can think of the dew point like this. The dew point is to what temperature would you cool the air such that you have 100% humidity, okay? What temperature do you cool the air such that you have 100% humidity? If the dew point temperature is close to the actual temperature, that means that you probably have very high humidity. If the dew point temperature is much lower than the actual temperature, that means your humidity is low, okay? Because you have to cool, but basically, like for example, if it's 80 degrees outside, but it's 50 degrees Fahrenheit dew point, that means you have to take that air at 80 degrees Fahrenheit, cool it all the way down to 50 before you have 100% humidity, okay? So, but it's a better measurement. The dew point doesn't lie. It always tells you pretty much an absolute amount of water that's in the air, okay? So that's a better measure in a lot of ways than relative humidity. All of these things are important to us as engineers because if you're an HVAC designer, okay, you've got to understand how humidity and how much water in the air affects the calculations that you do, okay? It's too significant to just ignore, okay? You can't just throw it out and say, I'm just going to assume all air is dry air and not worry about it, okay? It's too significant to ignore, so we have to take it into account, okay? We can use the humidity ratio, which I already defined before, to calculate the difference in enthalpy here of real air, which is H, versus dry air, which is the H dry air. The difference in enthalpy was very significant, and because you have to add in that extra term there, which is the omega times Hg, okay? That changes the enthalpy of the air. Basically what happens, and I think people have observed this, if you go somewhere really dry, right? If you go somewhere really dry, like the desert, in the summer, let's say, in the daytime, it heats up very quickly, right? And at nighttime, it cools off very quickly, right? In dry environments, it's easy to heat it up and it's easy to cool it off. Dry air is easy to heat up and easy to cool down. Moist air is a lot harder to heat up and a lot harder to cool down because you've got to not only heat the air, you also have to heat the water vapor, okay? So it does drastically change the thermodynamic calculations, okay? You can't just ignore it, all right? You can't just ignore it. For this purpose, all I want you to get out of this when you go into future classes, and you can take, I believe we have an HVAC type tech elective that you can get into more of this kind of stuff, and maybe you get into the HVAC industry. Maybe it's on the design side, maybe it's on the equipment side, whatever it is. all I need you to do when you leave this class is to have an appreciation and go, oh yeah, water vapor does have a big effect on the properties of air, and it's important that I understand it. And to have some experience with the psychrometric chart. That's what we're going to do here. Okay? So what I want to do is work with you, instead of doing all these calculations, with a calculator and formulas and things like that, most engineers use a psychrometric chart. It makes life a lot easier, okay? Because you can do all these thermodynamic calculations related to water vapor without having to do any numbers, or there's not a whole lot of calculations necessary. The chart can give you all the information you need, okay? The hard part about the chart, though, is it's a little bit tricky to read. There's a lot of lines and there's a lot of numbers on it, okay? So what I wanted to do is go through an example of how to read it and use it for certain values and certain things that we need. Okay, so I was thinking about the weather yesterday, and I thought, well, you know, yesterday it was probably about 25 degrees Celsius and about 40% humidity. So I thought, okay, let's use a psychrometric chart and let's calculate all those different things, all these different things with the psychrometric chart. Okay, so I've got to bring it up here. Okay. Let's see here. Get it. Almost there. I think it's at the end. Here it is now. Of course, they've got to turn it on me, so now I have to turn it. Okay, this should be good right there. What I want to do now is find where the point is on this chart that I'm interested in, okay? And it can be a little bit intimidating to look at this at first. Now, the two things I know is I know my temperature is 25 degrees Celsius, which, by the way, is, so, I don't know, 75 or 80 degrees Fahrenheit, somewhere in that range, okay? And my humidity, relative humidity, is 40%, okay? So what I'm going to first do is identify the 25 degrees Celsius. By the way, your chart says dry bulb temperature. If you look at the chart there on the bottom, it says dry bulb temperature. That's, this here is basically standard temperature, okay? Standard temperature we call dry bulb. That's as opposed to wet bulb, which I'll talk about in a moment, okay? So what I want you to do, and I'm going to do this the best I can in my thing here online, is I want you to, if you have a straight edge or use your book or something like that, to draw a vertical line that through 25 degrees Celsius. I'm going to try the best I can to do this, hopefully reasonably well. Something like that. Okay. Right. That's 25 degrees Celsius. Now I'm going to identify the point. If you look, the relative humidities are curves, right? They're curves that come down, right? You can see relative humidities are part of the curves, and I'm looking for the 40% one, and you can see where does the 40% curve intersect that line. It's pretty much at this point right here, which I've marked in red, okay? So find where the 40% relative humidity curve crosses the 25 degrees Celsius vertical line. That's the point where we're at on the psychrometric chart. Okay. On my chart, it's like a purple curve that goes 40%. Okay. Now, another thing I encourage you to do now is I'd like you to draw also a horizontal line that goes through that red point. So I'm going to try my best to do that. A horizontal line that goes through that same point. Let's see here, something like this. Okay? Draw a horizontal line like that. Okay? I'm gonna redo that a little bit. I'm gonna shorten that there, like that, just so that you can see that number, but you get the idea. I'm going to try to extend it a little bit, see if I can keep this somewhat straight. Okay, that's better. Well, you get the point. Okay. Okay, so let's now figure out how we read this chart. Let's go back to what do we want. First thing we want is the humidity ratio. Humidity ratio is given by omega. So we go back to the chart. The humidity ratio is actually given here on the right side of the chart. Okay, the humidity ratio is here. Okay, and so you'll see that there's different markings for it. And my horizontal line pretty much goes straight through the 8. Yours probably goes straight through the number 8 on the right side for humidity ratio. And if you can read yours carefully, I don't know how good that came out. If you read it carefully, it says humidity ratio, grams moisture per kilogram dry air. Okay? So what that's saying is 8 grams of water, it's really saying 8 grams of water per 1 kilogram dry air. Well, we don't express humidity ratio as grams over kilograms. We express humidity ratio as kilograms over kilograms. So really, this is going to be 0.008 kilograms H2O per 1 kilogram dry air. Okay? So we just read that off the chart. That's nice. This is pretty easy to do. Everybody see where I got that number on the right side of the chart there? We're good? Okay. Enthalpy. Now the enthalpy one is a little bit different. The enthalpy one is up here. Okay? Enthalpy H, kilojoules per kilogram dry air. And the enthalpy values are in diagonal lines that go from top left to bottom right. Okay? So you see these diagonal lines, right? So what you have to do is you have to kind of figure out where does my dot intersect the diagonal line that goes up that way. If you work on this carefully, and I'll do it as carefully as I can here, you will see, I believe, that the diagonal line, that diagonal line comes awfully close. Okay? The diagonal line that I just drew corresponds to 46 kilojoules per kilogram dry air. Okay? Pretty close. I think some may argue that it might be a slightly less than 46. If you draw that line down very carefully, it's probably a little less, but whatever, right? It's a chart. How good can we get? Right? So 46 kilojoules per kilogram dry air is probably about right for its enthalpy. By the way, if you have low humidity, it does affect that enthalpy value quite significantly. Just look, if you can, where my green line intersects the 10% relative humidity near the bottom. And if you follow that back up to the H value, you get an H of about 30. It looks like about 30. So just going from 10% humidity to 40% humidity, your enthalpy has gone up from 30 to 46. That's a 50% change in enthalpy. Okay? So, and that's not even that great a change in water vapor. If you had it all the way up to 100% humidity, if you go all the way to the top, your enthalpy is probably somewhere in the neighborhood of about 76. Okay? So from dry air to very moist air, your enthalpy can go from, in this case, 30 to 76. That's a pretty big range, right? That's why it's an important factor. You can't just throw it out typically when you do HVAC. Okay? Everybody see where I got that one? Pretty easy to read. We're good? Okay. Next one is the wet bulb temperature. That's typically given by TWB for wet bulb. Now, these days we don't really need the wet bulb temperature, okay? We can certainly read it off the charts, and we'll do that in a moment. But what the wet bulb temperature is we used to measure humidity using something called a psychrometer, and typically it was called a sling psychrometer, okay? Yeah, we used to sling it around, okay? It was almost like imagine a slingshot, but instead of using it to throw something, it just slings, right? It just spins. And what we used to do is we used to have two thermometers, okay? You had one thermometer, what was called the dry bulb. It was just a standard thermometer like you've seen your whole life. You probably used as a kid, stuck in your mouth when you had a fever or whatever, just this normal thermometer, okay? The other thermometer was also a normal thermometer, but we put it inside a wick that had some water on it. And they would, basically the wick would be just like some material that would enable you to absorb some water. And essentially what would happen is the water would evaporate when you spun it around. And when water evaporates, it cools, okay? That's why you sweat, right? Well, the reason you sweat when it gets hot outside is that you evaporate water. And evaporating water cools you down, okay? Well, same thing happens inside a psychrometer. The evaporating water inside the wet bulb cools. And when you do the sling psychrometer, you would get two temperatures. You would get the dry bulb temperature, which is your standard temperature like we all know. And then you'd also get this thing called the wet bulb temperature, which is basically, you can relate it to the humidity and everything else using this chart. Okay? So we used to use the wet bulb temperature to solve for the humidity and not vice versa. In this example, I'm using the humidity to solve for the wet bulb. Not really what we need anymore. Okay? Now, modern days, we don't use sling psychrometers anymore because we have electronics that can do the same thing. We have very simple electronics that can measure humidity in the air. We don't need to do that anymore. Okay, so the wet bulb is not really as critical anymore, but is still sometimes used in industry in the HVAC. Okay, so where is wet bulb on here? Well, if you look carefully, you see a dotted lines, okay? Dotted lines that are very close to being pretty much parallel to the enthalpy lines that we just did, okay? And if you look very carefully, the 25 wet bulb temperature is marked there. If the 25 is marked and the 15 is marked, I don't think the 20 is sort of marked. Yeah, the 20 is marked as well. So some of these but they're all little dotted lines. They're hard to see, but you can see the dotted lines. If you look really carefully, our red dot is kind of in between two of the dotted lines, but I'd say it's pretty close to 16. You see that? It's pretty close to the 16 one, right? The dotted line. It's probably a little bit greater than 16. I think I said in my other class 16.3. I don't know if I really know. Do I really know that 16.3? I don't know. Okay? I went with it, but 16.3. Okay. The next one is the dew point temperature. Okay? The dew point temperature can be read off the chart, but it's a little bit different. What you do with the dew point temperature is you take that same red dot that you have, and what you have to do is then you have to take that same amount of water vapor. The same amount of water vapor is on a horizontal blue line that I drew here. You take that same amount of water vapor and you take that horizontal line all the way over to 100% humidity. 100% humidity is the final curve on the left, okay? You'll notice the humidities go 10, 20, 30, 40, 50, 60, 70, 80, 90. And then the last curve there, they don't mark it, but it's 100% humidity, okay, that last curve. So what you do is you take the horizontal line, you take it all the way over to 100% humidity, and then you ask yourself, okay, what's the wet bulb temperature there? What's the wet bulb temperature for 100% humidity for that same amount of water vapor, that same horizontal line? What do you think? About 10? Yeah. I think it's about 10, right? It looks pretty close. I guess, again, somebody could probably argue that's a little bit bigger than 10, a little bit less than 11. It's somewhere between 10 and 11, but, yeah, you know, how close can you get? So we'll say it's 10, okay? So the dew point temperature, the chart gave us, TDP, was about 10 degrees Celsius. Okay. Specific volume. You can also read specific volume from the chart. As if the chart didn't have enough stuff on it, you can read specific volume. You'll notice specific volumes go from upper left down to lower right. Okay. They, you see numbers here. The one with 0.92 is marked 0.92 volume cubic meter per kilogram dry air. And then you've got 0.91, 0.9, 0.89, 0.88, 0.87, 0.86. And if you look carefully, my red dot is probably about halfway between the 0.85 and the 0.86. Okay? So I'm going to say we're pretty much at 0.855 for my specific volume. So that's going to be, specific volume is 0.855, and that's going to be meters cubed per kilogram dry air. 0.855. You can see that the specific volume of water can change, you know, somewhat significantly here, right? Some specific volume of air can change can change quite significantly here, right? You can go from up at the near the top 0.95 all the way down to near the bottom here about 0.78. So, by the way, everything here is at 1 atmosphere. If you have higher elevation, lower pressure, you have to have a new chart, okay? And they do make charts for, you know, higher elevation, lower pressure, okay? They make other charts. This book, they only gave you one, but I'm sure you could find lots of charts out there if you want to. Okay, so yeah.
So that's the specific volume of the wet air?
Yeah, it's of the real air. Yeah, the real air. The air that we're really feeling. That's a specific volume of the air. It's measured in meters cubed per kilogram dry air. Yeah. It's a little bit confusing because what we do is we do all our calculations per mass of the dry air, not per mass of the total air. It's a little bit weird that way, I know. But that is the wet, that is the total water. I mean, it's total air. That's not it's basically saying that's a specific volume of this air, which is air and water. Okay. And again, the nice thing about this is the chart's pretty easy to read. If I gave you a chart, you should be able to do this and read off the values you need. Last one, you can't exactly read this off the chart, but I thought it was interesting, and that is the vapor pressure. Okay? Remember, I told you that the total pressure of air is equal to the pressure of the dry air plus the pressure of the water, right? So what's the vapor pressure here? Okay? There are two different ways I can see very simply to calculate this, given the equations that you already have. Okay? If you take a look at the humidity equations, the easiest way to calculate the vapor pressure is to use the relative humidity right here, because the relative humidity is equal to the vapor pressure divided by basically the saturation pressure. Okay? So let's just use that. It's pretty easy calculation. Okay? It says here, the relative humidity is equal to the vapor pressure divided by the saturation pressure. Since I want to solve the vapor pressure, let me rewrite this, right? I can say the vapor pressure is equal to the relative humidity times the saturation pressure, right? And the relative humidity is 40%. So this is going to be 0.4 times the saturation pressure. So then the question is, how do I find the saturation pressure? Use the tables. Because the saturation pressure, PG, will be, look up water, look up the pressure of water, saturated water, okay, saturated water at 25 degrees Celsius, at that temperature. Look up saturated water at 25 degrees Celsius. So you go back to your tables, standard saturated water table. Oops, now I gotta rotate my view back. I gotta erase all my stuff. You go back to good old standard water, saturated water table. And you go here to 25 degrees Celsius. Saturated water, 25 degrees Celsius, has a vapor pressure, saturation pressure of 3.1698. So that's what you use. You just use that value, 3.1698. So this here becomes 0.4 of 3.1698 kilopascals. So all you have to do is do that calculation. If you run it in your calculator, 0.4 times 3.1698, you get about 1.27. You get 1.27 kilopascals. Okay. Now, remember, as I said here, total air is equal to the vapor pressure plus the dry air pressure. Well, total pressure is around 100 kPa, right? If total atmospheric pressure is around 100 kPa and the water vapor is only 1.27, the other 99-ish is dry air, okay? So most of the pressure that we have is from dry air, okay? Water doesn't change its pressure that much, okay, but a little bit, okay? In this case, it's maybe about 1%, okay, is that water vapor, okay? Most of it is dry air, okay? But water vapor inside air has a lot of effects that are important, and that's why we can't ignore it. We can't just throw it out or forget about it. And all I wanted you to do is just simply have an opportunity to be exposed to some of the concepts and the psychrometric chart.